You trust your senses to reveal reality, but your brain was built for chasing prey across the African savanna, not for comprehending galaxies or particles that defy logic. The fastest thing humans have ever built, Voyager 1, would need 73,000 years to just reach the next star, trapped by a cosmic speed limit we cannot break. If reality, at its core, is nothing like what we evolved to see, how far from the truth is our intuition, and what happens when the universe pushes us past the breaking point? A Maasai tracker kneels in the early morning light, eyes scanning the ground for the faintest sign, a single indentation in the dust, no wider than a fingernail. Within seconds, he identifies the animal, the direction it moved, and how long ago it passed, all from clues that would vanish to most. In a 2018 study, Maasai trackers in Tanzania correctly identified animal motion from sparse, flickering dots with 95% accuracy. Novices, by contrast, hovered near chance, barely 20%. Their brains, shaped by generations of life on the savanna, are tuned to read movement and scale at a glance, distances from meters to kilometers, speeds up to about 30 meters per second. This is the range where human perception is sharpest, where survival depended on spotting predators, prey, or rivals before they got too close. Neuroscientists have traced this ability to a patch of tissue in the brain called MTV5, a region specialized for detecting motion at these everyday speeds. But this system, so finely honed for the chase, falters when faced with the extremes of the universe. Try to imagine the path of an electron or the warping of space near a black hole, and intuition collapses. The same neural machinery that lets a Maasai herder read the land with uncanny precision simply cannot process the quantum fuzziness of particles or the mind-bending curvature of space-time. Cognitive scientist Donald Hoffman describes our perceptions as a kind of desktop interface, icons and windows that hide the true workings underneath. Our senses evolved not to reveal reality as it is, but to keep us alive. The world we experience is a useful illusion, a survival toolkit built for the Pleistocene, not for passing the rules of relativity or the mysteries of quantum mechanics. Even today, experiments in virtual reality show that when people are shown objects moving close to the speed of light, their brains misjudge what's happening by hundreds of %. No amount of training bridges the gap. The universe operates on scales and speeds our ancestors never encountered, and our minds are left grasping for answers with tools built for a different world. Nothing in the universe can outrun light. The speed of light, 299,792 kilometers per second, stands as an absolute ceiling, a built-in limit written into the fabric of reality itself. Even our most ambitious machines barely register on this cosmic speedometer. Voyager 1, launched in 1977 and now more than 24 billion kilometers from home, travels at just 17 kilometers per second. That is over 60,000 kilometers per hour, faster than any jet, faster than any bullet, yet still just a crawl on the galactic scale. At this pace, the journey to our nearest neighboring star, Proxima Centauri, would take Voyager 1 roughly 73,000 years. That is more than 12 times the span of all recorded human history. The numbers are staggering, but they are not just statistics. They define the walls of our cosmic prison. Light from Proxima Centauri takes 4.24 years to reach us. Voyager's faint signal, riding radio waves at light speed, takes more than 22 hours to cross the gulf back to Earth. With every hour that passes, the gap grows wider. The spacecraft's own project scientist, Edward Stone, often described the mission as humanity's outstretched hand into the void, an attempt to touch the stars, knowing full well the stars will never answer. In interviews, Stone reflected on the emotional weight of these distances. Voyager is a tiny spacecraft, but it carries the dreams of a planet, and yet it is utterly alone. The reality is blunt. No chemical rocket, no known propulsion can break the speed limit set by nature. Even the most radical concepts, such as fusion drives, antimatter engines, or laser sails, face obstacles that seem insurmountable. The laws of physics leave us stranded, confined to a thin shell of space around our sun. The Milky Way, with its hundreds of billions of stars, stretches far beyond our reach. The speed of light is not just a number, it is a boundary, as real as any wall. For now, and perhaps forever, we remain on an island in the cosmic ocean, separated from the rest of the universe by distances our minds can barely grasp. Somewhere, a radio signal travels outward, growing fainter with every kilometer, until it fades into the background hiss of the universe. The numbers that define our cosmic isolation are easy to recite: light years, kilometers per second, the ticking of distant clocks. But living with them is something else entirely. For most of human history, the night sky was a map of possibilities, each star a neighbor waiting to be reached. Now, those points of light are reminders of a distance that cannot be crossed, not by any ship, not by any message, not in 1,000 lifetimes. Astronauts have described looking down on Earth and feeling a sudden, overwhelming sense of separation. The planet is a blue marble, floating in darkness, fragile and alone. The International Space Station orbits just 400 kilometers above our heads, yet even that thin gap is enough to change the experience of time itself. For the Voyager team, the knowledge that their spacecraft will never reach another star is both a technical fact and a quiet ache. Edward Stone once called Voyager a message in a bottle cast into a cosmic ocean, knowing full well that no one may ever find it. Psychologists have studied the effects of this knowledge. When people confront the reality of cosmic distances, the most common reaction is not awe, but a kind of existential vertigo, a sense that the universe is too vast, too indifferent for human meaning to matter. Some respond with wonder, others with anxiety, but almost everyone feels the weight of isolation. The mind, shaped by millions of years of tribal life and close horizons, struggles to find its footing in a world where everything familiar is confined to a single speck of rock and water. And yet, there is a strange comfort in this perspective. The same laws that keep us grounded also connect us to every other corner of the cosmos. The atoms in our bodies were forged in ancient stars. The light that reaches our eyes began its journey long before our species even existed. To recognize our place is to accept both our limits and our inheritance, a universe that is not built for us, but in which we find ourselves, thinking, wondering, and reaching as far as we can. A GPS satellite circles Earth at nearly 14,000 kilometers per hour, locked in a ceaseless race above the clouds. Each day, its onboard atomic clock gains 7 microseconds compared to clocks on the ground, an error so tiny it seems meaningless. But for the engineers who built the system, this sliver of time is the difference between pinpoint navigation and total chaos. In the late 1970s, as the first GPS prototypes took shape, Air Force memos dismissed Einstein's relativity as an academic curiosity. Nanosecond errors are negligible, one project lead wrote in 1977. But the data told a different story. Test flights in 1979 showed positions drifting by up to 10 kilometers a day. The numbers didn't add up unless time itself was bending. The problem wasn't just speed. Gravity, too, warps the flow of time. On the ground, Earth's mass pulls on every second, slowing clocks ever so slightly. In orbit, farther from that grip, time runs a little faster. The satellite's motion, on the other hand, slows its clock thanks to special relativity. The two effects don't cancel, they add up to a net gain of 7 microseconds per day. That's enough to throw off missile guidance, air traffic, even the location of an ambulance in a city. By 1981, a classified memo warned, "Relativity fix or system fails." A team of physicists, led by a young navigation specialist, rewrote the software. They programmed every GPS satellite to correct its clock by exactly 38 microseconds each day, subtracting 45 microseconds for gravity, adding 38 microseconds for speed, and leaving a net correction of 7 microseconds. The fix worked. Suddenly, the system snapped into focus. Positions locked within meters. Planes landed safely in fog. Emergency crews found accident scenes in seconds. The equations Einstein scribbled in 1905 and 1915 now guide millions of drivers, hikers, and pilots every minute. Even the International Space Station, orbiting just 400 kilometers up, feels the effects. Astronauts age 0.007 seconds slower every 6 months than their twins on Earth. Time dilation isn't science fiction, it's a daily fact, written in the code that guides every GPS receiver, every smartphone, every rescue operation. The geometry of space-time, once an abstract idea, has become a tool for finding our way home. Gravity, as Einstein saw it, was not a force at all. It was a bending of geometry itself, a warping of the stage on which every object moves. Imagine a heavy bowling ball resting on a stretched trampoline. The fabric curves, and marbles rolling nearby spiral inward, following the curves, not because they are pulled, but because space itself is sloped beneath them. This is the heart of general relativity. Mass tells space how to curve, and curved space tells matter how to move. Physicist Carlo Rovelli describes this as a radical shift, one that asks us to let go of the idea of invisible hands pulling on planets. Instead, Earth orbits the Sun not because it is being tugged, but because the Sun bends space-time into a well, and Earth's path simply follows the straightest line in that curved landscape. The familiar laws of motion, so reliable on the savannah, become unreliable when the ground beneath our feet is warped by mass and energy. Proof came not from theory alone, but from the heavens. For decades, astronomers puzzled over the orbit of Mercury. Its path around the Sun drifted by 43 arcseconds per century, more than Newton's laws could explain, a tiny sliver, but persistent. Einstein's equations predicted exactly this anomaly. The universe had revealed, in the slow precession of a planet, the fingerprints of curved space. Then, in 1919, the world watched as British astronomer Arthur Eddington led an expedition to the island of Principe, off the coast of Africa. During a total solar eclipse, Eddington's team measured the positions of stars whose light grazed the Sun. The starlight bent by 1.75 arcseconds, just as Einstein predicted. Newspapers declared, "Lights all askew in the heavens." For the first time, the geometry of space was not a mathematical abstraction, but a measured fact, visible in the sky. Today, the bending of light by gravity is seen in the arcs and rings captured by the Hubble Space Telescope. These Einstein rings, perfect circles of light, appear when a massive galaxy bends the light of a more distant one directly behind it. The cosmos itself becomes a lens, curving the straight lines of starlight into elegant, impossible shapes. Each arc is a signature of space-time's hidden geometry, a silent testament that the universe is stranger and more beautiful than our ancestors ever imagined. Time, so familiar in daily life, reveals itself as something far stranger when examined closely. The ticking of a clock, the rhythm of a heartbeat, the memory of a childhood afternoon, each feels anchored, absolute. But physics tells a different story. Time is not a river flowing the same for all, but a web of relationships. Each observer, each clock, each heartbeat is woven into its own fabric of moments, shaped by speed, by gravity, by place. Carlo Rovelli, a physicist who has spent decades studying the nature of time, puts it simply: the world is not a collection of things, it is a collection of events. In his view, time does not exist as a single thread stretching from past to future. Instead, it's a tapestry of happenings, each linked to others by the laws of the universe, but never quite the same from one vantage point to another. There is no universal now, only a chorus of local times, each singing its own tune. Stand on Earth, and your seconds are shaped by the planet's mass, by your distance from the center, by your motion through space. Move faster or climb higher, and time slips ever so slightly from the grip of your expectations. On the International Space Station, an astronaut's clock runs a little slower than those below. Near a black hole, time stretches and nearly stops, not as a trick of the mind, but as a fact of geometry. Rovelli writes, "We do not live in a world of things, we live in a world of events. Each event, each heartbeat, each breath, each sunrise exists in relation to all the others. Our sense of time, so solid in memory and routine, is only a rough map of a landscape that bends and twists beyond our understanding. What feels fixed is, in reality, always in motion, always relative to something else. To accept this is not to lose our place in the world, but to see it anew. The universe does not unfold by the clock on the wall. It opens in 1,000 different ways, from 1,000 different perspectives, each as real as the next. Time is not a single story, but a conversation, ongoing and unfinished, between every event that has ever happened and every event still to come. Vera Rubin spent countless nights at the Kitt Peak Observatory in the 1970s, staring at the swirling arms of distant galaxies. She wasn't looking for new stars or nebulae, she was tracking how fast galaxies spun. The expectation, based on Newton's laws, was simple. Stars farther from the center should orbit more slowly, just as planets farther from the sun move more leisurely. But Rubin's data told a different story. The outer stars whipped around at nearly the same speed as those near the core, defying every prediction. Night after night, the numbers stayed flat. Rubin's notebooks filled with straight lines where there should have been curves. She wrote, "They said galaxies can't defy Newton. I measured them anyway." The only explanation was that something invisible, something massive, was holding these galaxies together. This unseen matter, now called dark matter, outweighs all the stars and planets we can see by a factor of 5. It forms vast halos around every galaxy, shaping the cosmic web itself. The evidence didn't stop with Rubin. In 2006, astronomers watched 2 galaxy clusters collide in the Bullet Cluster. The visible gas clouds slammed together and slowed down, but the bulk of the mass, mapped by how it bent background starlight, kept moving straight through, untouched. The lensing patterns revealed that most of the matter was invisible, passing through like ghosts. No telescope, no detector has ever seen a single dark matter particle directly. Yet its gravitational fingerprint is everywhere, from the rotation of galaxies to the bending of light across billions of light years. If dark matter is the universe's hidden scaffolding, dark energy is its silent engine. In 1998, Saul Perlmutter and his team tracked distant Type Ia supernovae, expecting to find that cosmic expansion was slowing under gravity's pull. Instead, the supernovae appeared dimmer than predicted, evidence that the universe's expansion was speeding up, not slowing down. The discovery shocked the scientific world. Gravity, it seemed, had lost control. Today, dark energy is thought to make up 68% of the universe's total energy. Its nature remains a mystery. It isn't a force like gravity or electromagnetism, but a property of space itself, a kind of cosmic repulsion that grows stronger as the universe expands. Together, dark matter and dark energy dominate the cosmos. Ordinary atoms, everything we see, touch, and measure, make up less than 5%. The rest is hidden, detectable only through its effects. We live in a universe where almost everything is invisible, its true nature still out of reach, waiting to be understood. A single photon leaves a mark on a detector, but until that moment, quantum theory says it travels every path at once, through both slits, around both corners, neither here nor there. In 1801, Thomas Young's double-slit experiment revealed the first hint. Light, when not watched, creates a pattern of waves interfering. but fire photons one at a time, and the same pattern slowly appears, as if each particle explores all possibilities, interfering with itself. Try to catch the photon in the act, set up a detector to see which slit it chooses, and the pattern vanishes. The act of looking decides the outcome. This is superposition, the quantum rule that a particle can exist in many states at once until measured. In the 1920s, Erwin Schrödinger built his famous cat-in-a-box thought experiment around it. Until you open the lid, the cat is both alive and dead, a blend of all possibilities. For decades, physicists argued whether this was a real feature of nature or just a mathematical trick. Then, in the 1970s and 80s, experiments began to probe the heart of the mystery. Enter Alain Aspect and, later, Anton Zeilinger, physicists who turned quantum weirdness from philosophy into laboratory fact. In 1982, Aspect's team in Orsay, France, fired pairs of entangled photons to distant detectors. Measure one, and the other's state snaps into place instantly, even if separated by kilometers. The results violated Bell's inequalities, rules that any classical local reality must obey. Einstein called it spooky action at a distance, but experiment after experiment confirmed particles can be linked by correlations that defy all common sense. Zeilinger, awarded the Nobel Prize in 2022, described it with a grin. The world is not as it seems. Reality is decided when we look. Superposition and entanglement aren't just quirks, they're the foundation of quantum mechanics. The double-slit experiment shows a particle is a wave of probabilities until observed. Entanglement shows that particles, once connected, remain linked across space, their fates intertwined. Every time a quantum system is measured, the outcome is conjured from a haze of possibilities. The universe at its smallest scales refuses to be pinned down. Certainty is a luxury of the everyday world. At the quantum level, reality is a game of cosmic dice, played behind a curtain we can never fully lift. Anton Zeilinger, a physicist who spent decades peering into the quantum world, once said with a smile, "The world is not as it seems. Reality is decided when we look." For most of history, people assumed the universe existed independently, ticking along whether or not anyone was there to watch. But the experiments of the last century have left that old certainty on shaky ground. Every measurement, every act of observation seems to play a part in shaping what actually happens. A photon is everywhere and nowhere until it leaves a trace on a detector. Two entangled particles, separated by billions of kilometers, remain linked until one is measured. Then both snap into definite states, as if the universe itself was waiting for a decision. Physicists like Zeilinger have shown, again and again, that the outcome isn't fixed until someone checks. Even the question of which property to measure, direction, position, spin, changes the answer you get. It's tempting to imagine that uncertainty is just a matter of ignorance, a gap that better instruments or sharper minds could close. But quantum theory doesn't allow for hidden facts waiting to be found. Instead, it insists that possibilities are real and only collapse into a single outcome when observed. The world is not a stage set, waiting for us to arrive. It's more like a script that isn't written until the curtain rises. Where does this leave our search for certainty? The more we learn about the fundamental rules, the more it seems that reality is not simply out there, but arises in the act of questioning itself. Zeilinger's words echo a deeper puzzle. If observation shapes reality, what does it mean to know anything for sure? If the universe waits for us to look, are we part of the story in ways we never imagined? At the edge of knowledge, the questions multiply. Is reality a fixed landscape, or a tapestry woven from every act of attention? Can the world exist without someone to witness it? Or is the act of looking, of asking, woven into the fabric of everything that happens? The quantum world doesn't offer easy answers, only the invitation to wonder. As Zeilinger put it, What we perceive as reality now depends on our earlier decision what to measure, which is a very, very deep message about the nature of reality and our part in the whole universe. A black hole just 10 times the mass of the Sun compresses all that matter into a sphere only 30 kilometers wide. At its edge, the event horizon, gravity reaches a level that defies all human experience. The difference in gravitational pull between your head and your feet, just 2 meters apart, can exceed 1,000,000 times Earth's gravity. No body, no molecule can survive such a gradient. The atoms themselves are torn apart. Physicists call it spaghettification. You are stretched lengthwise and squeezed sideways, pulled into a strand thinner than a human hair and longer than a skyscraper. For a stellar mass black hole, this happens thousands of kilometers before you even reach the horizon. The numbers come straight from Einstein's equations. The Schwarzschild solution tells us exactly where the point of no return lies, and just how lethal the tides become. Yet in the heart of a supermassive black hole, millions of times heavier, the same horizon is gentle. A person could cross it without feeling a thing, only to meet their end much deeper inside. Stephen Hawking once joked that falling into a black hole would be the ultimate science experiment. You would glimpse the edge of physics, where space and time themselves are pulled to a breaking point. In the first fraction of a second after the Big Bang, the universe expanded by a factor of e to the 60th power, growing from subatomic size to something as large as a grapefruit in just 10 to the minus 32 seconds. This burst, known as inflation, smoothed out temperature differences across the cosmos and left behind the cosmic microwave background, a faint glow that's nearly uniform in every direction. Yet the smoothness is almost too perfect. Measurements from the Planck satellite showed temperature variations of only 1 part in 100,000, even between regions that could never have communicated. But the puzzle deepens. Quantum field theory predicts that empty space should be packed with energy, enough to blow the universe apart instantly. The numbers don't just fail to match observation, they miss by a factor of 10 to the 120th power. No other calculation in science is off by so much. Anna Lindner, a physicist who helped shape the theory of inflation, calls it the worst theoretical prediction in the history of physics. The universe's expansion, the smoothness of the background, and the vacuum energy gap all point to a reality that refuses to line up with our best equations. Between the smallest scales, the Planck length of 10 to the minus 35 meters, and the largest, stretching 46 billion light-years, lies a span of 61 orders of magnitude. Somewhere in this vast gulf, our understanding breaks down, and the numbers stop making sense. The numbers that shape our universe are more fragile than they appear. Shift the strength of the strong nuclear force by just 2%, and the stars would never forge carbon. A tweak in the fine structure constant, even by a few percent, and chemistry as we know it collapses. No stable atoms, no water, no life. These razor-thin margins have fueled decades of debate. Some physicists run simulations by the thousands, asking how often do the dials land just right. The odds, by some counts, are less than 1 in a trillion. Others argue the question is meaningless. If there are countless universes, each with different rules, we simply find ourselves in one where life is possible. But the puzzle runs deeper. The universe began in an incredibly organized state, with entropy at its lowest. Every second since, disorder has grown, setting the arrow of time in motion. Memories form, stars burn out, glasses shatter, but never unbreak. David Albert, a philosopher who studies the foundations of physics, calls this the most profound mystery. Why did the universe start so improbably tidy? Without that low entropy beginning, there would be no past, no future, no story to tell. In this light, reality feels less like a given, more like a question, one that stares back at us with every breath, every heartbeat, every silent night under the stars. Albert Einstein once wrote, The most incomprehensible thing about the universe is that it is comprehensible. Yet standing at the edge of what science has uncovered, comprehension feels like a fragile thing. The more we discover, the more the familiar world recedes, replaced by rules that seem to contradict every instinct we carry from our ancient past. A mind tuned for the hunt now tries to fathom particles that flicker in and out of existence, or a cosmos that expands faster than light, or a fabric of space that bends and twists under the weight of invisible mass. Every answer opens onto new questions. What lies beyond the horizon we can never reach? Is the universe a single story, or one among countless possibilities? Are the laws that govern our world fixed, or do they shimmer with uncertainty, depending on how and where we look? Even the act of observation, so simple in daily life, becomes a mystery. Does the universe exist without someone to witness it, or is reality itself woven from the act of looking? Einstein's words linger, not as a declaration, but as an invitation. To wonder at a world that both reveals and hides itself, to accept that not every question will find an answer. In the end, perhaps the greatest mystery is not out there among the stars, but within the mind that seeks to understand. Right now, over 95% of the universe remains invisible and unexplained, while every smartphone relies on quantum rules we barely grasp. As physics shatters old certainties, our capacity to adapt, to question what we know, becomes our most critical tool. In an age defined by unprecedented discovery, reality isn't what it seems. The future belongs to those willing to wonder, not just accept. What are you still certain of?